Hello friends, welcome to G-Centric. So in this lecture, we will study about ideal transformer. Okay, so basically this ideal transformer means we will not include losses, right? Losses are neglected. That is why we call it as ideal transformer. How much ever current is generated, that much amount of flux will also be generated. Okay, so there will be no copper losses or iron losses. We will not consider for this one. So now, how does this ideal transformer look? Okay, so we will draw a transformer. This is primary coil. Okay, and here is the secondary coil. In between, this is the transformer. Okay, so this is a symbol of the transformer. Now there will be V1 voltage. Okay, this is current I1, and this is dot convention. Here also dot convention. Now keep it in mind that this is V2. The direction of the current is in this way. Okay, I2. Now we have got the turn ratios N1 is to N2. Okay, now this direction, this dot convention, we will put a door over, we will see from the opposite side whether the current is entering or leaving. So here the current is entering, okay, and here the current is leaving. Okay, so this is the symbol for ideal transformer where mutual effect will be negative. If you take both as entering, then we will not call that as ideal transformer. Okay, I think till here the concept is clear. Now we know that V2 by V1 equal to N2 upon N1 equal to I1 upon I2. Okay, so this current will always go opposite with voltage and the number of ratio turn. Okay, so let us take this as something called as A. This is the turn ratio. Okay, so this much you have to keep in mind for the ideal transformer. Now coming to the two-port network of this diagram. Okay, so how will be the two-port network? Okay, we will see the two-port network for this one. Now I will draw the transformer again. Okay, so this is one coil, this is secondary coil. Okay, turn ratio is N1 is to N2. This is current I1 and this is voltage V1, V2, and the direction of the current should be in this way, right? For in the two-port network we have seen this direction. Now what will be the equations? Equations will remain same. N2 by N1 equal to I1 by I2 equal to A. But since the direction of the current is taking opposite from the ideal transformer, we will have a negative sign for the current I2. Okay, so this is for the two-port network. And some questions will be asked based on this concept. Okay, and here also the dot convention will be like this. Okay, so now we will see one more problem based on ideal transformer where we will use the concept of two-port network. Okay, so given in this question 235, we have to find all the parameters related to this ideal transformer. Okay, so now if you see here, first we will check whether it is the ideal transformer. The current is entering and the current is leaving, so the mutual effect is negative. Okay, now this is dot convention they have given, this is transformer, and we know that V2 upon V1 equal to N2 upon N1 equal to I1 upon I2 equals to A. Okay, so first we have to find the Z parameter. Okay, so what is the Z parameter say? Okay, Z parameter. How do we write Z parameter? V1 equal to Z11 I1 plus Z12 I2. Right? Then V2 is equal to Z21 I1 plus Z22 I2. Right? This is the equation for the Z parameter. Now to calculate V2, I can equate this as V2 by V1. Okay, this turn ratio is nothing but N2 upon N1. Right? So N by 1. So V2 upon V1 is equal to N. I1 upon I2 equal to N. So if you see here, V2 is equal to V1 times N and I1 will be I2 times of N. But we cannot rearrange these equations in this form. It is impossible to arrange. So what we will conclude is that Z parameter does not exist for the ideal transformer. Okay, so for ideal transformer, the Z parameter does not exist. Next, coming to the Y parameter, similarly here also we will get, okay, we cannot rearrange in this one also because we have I1 I1 equal to V11 Y11 V1 plus Y12 V2 and I2 is equal to Y21 V2 plus V22 V2, right? So here also if you take again V2 will be equal to n times V1 and I1 will be equal to n times I2. So this also you cannot arrange in terms of V1 and V2, right? So here if you take over here, what will you get? Again a V2 by V1. So therefore Y parameter does not exist for ideal transformer. Okay, next we have solved the two parameters. Coming to the ABCD parameter, how do we calculate it? So we know the equations for this one, right? So V1 equal to A V2 plus BI2. Okay, this was minus, okay, and here I1 is equal to CV2 minus DI2. Now since the direction of the current is similar for the power system, okay, then we will take here as plus. Okay, so now we can rearrange this one, right, in this form. V2 upon V1 is equal to N. Okay, so we want in the form of V1, right? So V1 will be equal to V2 by N, and this will we can assume as 0 I2. Similarly for I1 we can take it as N times I2, right? So we will assume for this 0 V2 plus N times I2. Okay, so our ABCD parameter will be A is how much? 1 by N, B is 0, this is 0 and this is N. Okay, so this is the ABCD parameter and we are left with H parameter. Okay, we will see up the H parameter. H parameter, and what are the equations we will write for this one? V1 and I2, right? So here we will get okay, so here we will get H11 I1 plus H12 V2, right? Here also H21 I1 plus H22 V2. Okay, so this is the parameter. Next V1, we already have V1, that is V1 is equal to, okay, how do we write? N times of, this is V2 by V1 equal to N. So we want in terms of V1, so this will be V2 by N, right? So this is V2 by N and here it is 0 I1. So our H parameter, we got first two parameters. This is I1 0 and we have here, we will take this as minus now because it is the opposite direction, right? So here it will be minus 1 by N. Okay, next coming to this I2. So we know I2 by I1 equal to 1 by N. Okay, so we want I2. So I2 will be I1 upon N. Okay, so I2 is equal to I1 upon N plus 0 V2. Okay, and this is minus. Okay, we have to take in this direction, right? First we have to arrange V2. 0 V2 minus, this is minus, okay, I2, H11 I1 V2. Okay, here only we will having the minus sign, right? So this will be plus and this is minus. Okay, so we have here as minus 1 by N 0. Okay, so this is the H parameter for this question. Alright, so next we will see few more problems, some concept and few more problems based on those concepts. Okay, so coming to this question, before that in the previous question in the H parameter, okay, B parameter will be plus 1 by N because voltage is positive but the direction of the current is negative. Hence the C parameter will be minus 1 by N. Please make that correction in the previous question. So next coming to this one, determine the value of K for series resonance. So now if you see all over in this circuit there is no K available. So how to derive this one? Now we know that it is the concept of series resonance, okay, and the concept of mutually coupled. So from the series concept, okay, series resonance concept, we know that XC equivalent will be equal to XL equivalent, right? Now we have to see this was nothing but how much is, there is only one C available. So we will take J12 equal to XL equivalent. Okay, so this XL can be written as omega L equivalent, right? X is equal to omega L. And this will be equal to J12 ohms. Right, so this is one of the equation we arrived from series resonance. Now if you see here, to find the L equivalent, we cannot add directly 8 and 8 ohms. That is not equal to 16 ohms. That is because there will be a mutual effect because of this dot convention in both the coils. Right, so now we know what is, these are opposing, series opposing, right? One, if the current is flowing in this way, then the current is entering, and one more from here the current will be leaving, right? So this is the concept, and hence since it is series opposing, right? We know the formula for the series opposing, nothing but L equivalent is L1 plus L2 minus 2M. So this is the formula for finding the L equivalent when we have series opposing. Okay, so now this L equivalent I can multiply whole this equation with omega L equivalent, omega L1 plus omega L2 minus 2 omega M. Now this I will replace M, right? We remember in the first class itself we have derived the relation between K, L and M. So it will be equal to omega L2 minus 2 omega K L1 L2. So this is the relation. Now if this omega, if I take inside, it will be omega square, right? So one omega I will multiply with L1 and the other omega I will multiply with L2. Okay. Now omega L equivalent, we know it is 12 ohms, right? It is 12. Next omega L1 is, if this is, we will consider as L1 and this is as L2. Okay. So we will get 8 plus 8 minus 2 K, 8 into 8. So this is 12, 16 minus 16K, right? 16K will be equal to 4, K is equal to 1 by 4. So this is the value of the K, and we know that K will lie in between the range of 0 to 1. So this 1 by 4 is in between 0 to 1. Okay, so this is how we will solve this question. The concept of series resonance, concept of series opposing, and the concept of mutual effect. Okay, so this is the question solution for this question. Okay, so now we will see the referring sides. Okay, this is useful for the electrical machines where we will refer the primary side of the transformer parameters to the secondary parameters, or it is either way. We will take the secondary parameters to the primary parameter. So we will say referring secondary parameters to primary, or referring primary parameters to secondary parameters. So first we will see, okay, secondary referred to primary. Okay, so we will shift all the secondary parameters to the primary. Now what is the formula to do that? Okay, so if any of the parameters, now we will take first one as load. Okay, so we will shift this load ZL to the primary. We will refer it to the primary. How we will do? ZL will be equal to referred to, okay, referred from whole square into ZL. Okay, so while we are referring, we will take this as ZL dash, or else we will take it as actual value. Okay, so here we will take some parameter. Okay, so when you are referring to something, parameter dash, it will be equal to referred from whole square into actual value. Now this whole square will only come for resistor and impedance. If you are referring voltage and current, this square will not exist. Okay, so now we will see over here. So now if I have to refer this load to ZL dash, we'll take it to primary, then referred to means we are referring to the primary. See, the turn ratio is N1, right? By referred from secondary, we are referring to the primary, right? So we will take this as N2. Now since this is the impedance load, we will take whole square. And what is its actual value? Nothing but ZL. Okay, this is for the load. Now if I have to shift V2, Okay, let us take here, we have voltage V2. If I have to refer it to the primary, I'll write V2 dash referred from into its actual value. There is no square for this term. Next, similarly for I2, I will take N2 by N1 into I2. Okay, current, it will always go in the reverse order. So these are the secondary parameters referred to the primary parameters. Similarly, now we will refer primary to secondary parameters. Okay, so we have V1 dash is equal to N2 by N1 times V1. Similarly, I1 dash is nothing but N1 upon N2 into I1. Okay, then we have got resistor load, right? R1. R1 dash is equal to N2 by N1. Now we will have square over here into R1. Okay, so this is about the referring of the parameters from primary and secondary and vice versa. Okay, so now we will see one question based on this concept. Okay, so coming to this question number 237, we have to find Vyy dash over here and attenuator factor is 0.8. Okay, so the attenuator factor is only this much, that means 0.8 of this will not be considered. Okay, so we have to find from here to here, which is 0.8. Okay, so we have to find that 0.8 times the factor of this voltage, that is Vyy dash. What we have to do is, first we have to get this voltage of the secondary side. So once this voltage is known, then we can multiply that voltage with 0.8 times. So this voltage will be known. Okay. To do that, now we have referred the parameters from primary to secondary. Okay. We have here V1 dash. Okay. So this is referred to this one. However, how we have to do it? Referred to, that is 1.25, referred from times the actual value, right? So we will get this as 125 volts. Okay, so now this Vyy dash will be equal to 0.8 times of 125 volts. Okay, so 12.5, you'll get 1, 2, 5, 8, 8 5s are 40, 16, 20, 8 1s are 8, 9, 10. So this is 100 volts. Okay, so the Vyy dash value of this voltage across this one, which has the 0.8 attenuation factor, is 100 volts. Coming to this, when it goes in the reverse way, right, what is the value of this one? V1. Okay, so for that one directly there is nothing, we will directly refer it to as 100 volts. Okay, so if it is 100 volts, then this voltage will appear over here. So this is nothing but, let us call it as V2. Okay, so now we are referring from secondary to primary, right? So we have referred to upon referred into 100 actual value, right? So this will be 1000 upon 125. So you will get, okay, 125 times 8 is 100. So 1080, 1000 is 125. Okay, so this is 80 volts. Okay, so this is about the concept of referring parameter. Now there is a small concept that is based on the energy stored. Okay, so let me write it over here. Energy stored in the mutually coupled coils. Energy in coupled coils. Okay, so this is the last concept in this ideal transformer. Now what is the energy stored? We will take it as W half, if there are L1 and L2 coils, L1 I1 square plus half L2 I2 square. Okay, so now the thing is that here plus or minus. Okay, then we'll write M I1 I2. Okay, so this plus, when it will come? When we have M is positive. Okay, and this negative will be appearing when we have M is negative. Okay, so this is the concept of the energy. So in the next lecture, we will see some problems whole on this dot convention mutually coupled and some energy stored as well as on the referring parameters. And then we will finish this magnetically coupled circuit chapter. Okay, so this is not important in gate time point of view, but this is very helpful for the electrical machines. Okay, so this will form the base for the electrical machines. Okay, thank you.